Imagine this. A customer taps the pay button on your app. The screen freezes for a second, so they tap again. 2 seconds later, 2 charges of $50 appear on their bank statement. The customer calls support, angry. Support pings engineering. Engineering pings you. And somewhere, a Google or Amazon interviewer is asking another candidate the exact same question, because this scenario, the duplicate charge, is the single most common payments bug in the world. Today we are going to design the system that makes this bug impossible. Not at a high level. At the level a senior engineer would defend on a whiteboard in a FAANG low-level design interview. By the end of this video you will have a complete script, a set of diagrams, and a checklist you can repeat from memory in any payments interview. Before we touch any design, understand how you are actually being scored. The interviewer is not waiting to hear the word idempotency. They are watching for 5 specific signals, and most candidates only show 2 or 3. Signal 1. You bring up duplicate prevention in the first 3 minutes, before they hint at it. Signal 2. You talk about what goes wrong, not what goes right. Senior engineers think in failure modes. Signal 3. You explicitly point at the whiteboard and say, this is inside the database transaction, this is outside. Boundaries matter. Signal 4. You mention observability, alerts, and on-call without being asked. Real systems have humans behind them. Signal 5. The pseudocode you write looks like real production code, with error handling and logging, not like a tutorial snippet. Hit 4 out of 5 and you pass. Hit all 5 and the interviewer writes strong higher on the feedback form. Now the one-sentence definition you will memorize for the rest of your career. An operation is idempotent when performing it once and performing it 10 times produce the exact same effect on the system. Press an elevator button 10 times. The elevator still comes once. Open a file 10 times. It is still open exactly once. Pay $50 10 times with the same intent. The customer is charged exactly once. This is stronger than just safe retries. It says the final state of the system after attempt 10 is byte for byte identical to the final state after attempt 1. Now contrast with the opposite. Adding 1 to a counter is not idempotent. Sending an email is not idempotent. And here is the key insight. Charging a credit card is naturally not idempotent. Money moves every call. Our job as engineers is to wrap a non-idempotent operation in a layer that makes it behave as if it were. That layer is what we are building today. Duplicates are not user mistakes. They are physics. Networks are unreliable, and your system has to absorb that. There are 4 real sources, and every payment engineer has seen all 4. Source 1. The user double taps the pay button because the first tap gave no visible feedback. Loading spinners help, but humans are impatient. Source 2. The mobile network drops the response packet. Your server already processed the charge, but the client never heard back. The client library, doing the correct thing, retries. Source 3. The user hits the browser back button and the form reposts. Browsers warn about this, but plenty of users click OK. Source 4. The payment gateway sends you a webhook saying the charge succeeded. Your acknowledgement is slow, the gateway gives up, and retries the same webhook. Memorize these 4 sources. In the interview, when asked why duplicates happen, list all 4 before the interviewer finishes the question. Never say the user is dumb. Say the network is unreliable and our job is to make the system tolerant. Now the API contract, the first thing you draw on the whiteboard. 1 endpoint, post/payments. Request body, amount, currency, customer ID, payment method, order ID. 1 critical header, idempotency-key, a UUID version 4 generated by the client before the first attempt. Response, 201 created on first call with the payment object, 200 OK on every retry with the exact same payment object, 409 conflict if the same key arrives while the first request is still in progress, 422 unprocessable if the same key arrives with a different request body. For properties of the key you must defend. 1. Generated by the client, never by the server. The server cannot retry a request it has not seen. 2. A UUID version 4, 122 bits of entropy, no collision risk at any scale. 3. Scoped per customer. The same key from two different customers is two different requests. 4. Lifetime of 24 hours. After that the dedup record can be deleted. Real retries do not happen days later. The idempotency key is not a flag. It is a state machine with 4 states, and the state machine is the heart of the entire design. State 1, new. The key has never been seen. We insert it and start processing. State 2, in_progress. A request is currently running. This is the most important state, and the one juniors forget. If a duplicate arrives while we are in in_progress, we either wait, or return 409 conflict with a retry after header. If we skip this state, two duplicate requests can both pass the existence check at the same millisecond, and we double charge. State 3, completed. The first request finished, the full response body is stored. Any retry now returns the stored response immediately, no processing. State 4, failed. Terminal error. The client must generate a new key to try again. Draw this 4-state diagram on the whiteboard. The in_progress state, with the concurrent duplicate scenario, is what separates senior answers from junior ones in this interview. Where do you store the keys, and what does the table look like? 3 storage options, and you must compare them. Redis, microsecond reads, TTL is native, perfect for the hot dedup check, but Redis can lose data on failover and is not transactional with your payments table. DynamoDB, durable, single-digit millisecond latency, conditional writes give you native dedup, perfect on AWS. Postgres, durable, fully transactional, lets you commit the idempotency row and the payments row in one atomic transaction. Slowest of the 3 but the safest. The senior answer for a FAANG interview, Postgres is the source of truth because money belongs in a database, Redis only as an optional hot cache in front for read-heavy retries. Never the other way. Now the schema. Table idempotency keys. Columns, key varchar 64 primary key, customer ID indexed, status enum of new in progress completed failed, request hash char 64 storing the SHA 256 of the canonical body, response body job, created at, expires at. Unique constraint on key plus customer ID. A daily cleanup job deletes rows past expires at. 6 columns, 1 unique index, 1 cleanup job. That is the whole dedup substrate. Now the dedup middleware in 10 lines, line by line, the version you write on the whiteboard. Line 1. Read the idempotency-key header. If missing, return 400 bad request. Line 2. Compute SHA 256 of the canonical request body. Canonical means sorted keys, no white space, deterministic. Line 3. Begin database transaction. Line 4. Insert into idempotency keys with onConflict do nothing. If insert succeeded, this is a brand new key, fall through to processing. Line 5. If insert returned 0 rows, select the existing row for update. Line 6. If status is completed and the stored request hash matches the new request hash, commit and return the stored response body. Line 7. If status is completed but hashes differ, commit and return 422 with a clear error code, idempotency key reuse with mismatched payload. This catches client bugs early. Line 8. If status is in_progress, commit and return 409 conflict with a retry after header of 1 second. Line 9. Process the payment, update the idempotency row to completed with the response body, commit. Line 10. Return the response. 10 lines, every failure mode covered. Transaction boundaries. This is where most candidates lose half the points in this interview, and it is the easiest place to stand out. The rule, external network calls never go inside a database transaction. The charge call to Stripe takes hundreds of milliseconds and can fail. If you wrap it inside begin and commit, you hold row-level locks for hundreds of milliseconds, throughput collapses, and a Stripe outage takes your database down with it. So what does go inside the transaction? Exactly 3 writes. The idempotency row update. the payments row insert, an outbox event row insert. All three commit atomically, or none do. What goes outside? The actual call to the payment gateway, performed by a separate background worker. This pattern, the outbox pattern, is the most important pattern in this design. Inside one transaction, write payments row status pending plus outbox row containing charge this card, amount, idempotency key for the gateway. The worker pulls the outbox every second, picks up pending rows, calls Stripe, on success updates the payments row to captured and marks the outbox row done. The database is the single source of truth. The external world is async and retry safe. This is exactly how Stripe, Uber, and Amazon process payments at scale. Concurrency. Two duplicate requests with the same idempotency key arrive in the same millisecond. Both pass the initial existence check, both try to insert, one wins, one loses. How does your design handle this safely? Two approaches you must compare. Pessimistic locking. Select for update on the idempotency row. The second request blocks until the first commits, then rereads the row, sees status completed, returns the stored response. Simple, correct, but holds a row lock through the entire handler, including any external call. Bad for throughput. Optimistic concurrency. Use the unique constraint on the key column as your lock. Insert with onConflict do nothing. The losing request gets 0 rows from the insert, knows it lost the race, falls into the retry path, reads the completed row, returns the stored response. No row locks held, just a unique index check by the database. For payments at FAANG scale, optimistic with the unique index is the right answer. Cite Postgres on conflict or DynamoDB conditional writes specifically. The interviewer is checking whether you understand that database constraints can act as a distributed lock without the operational cost of a real lock. Now we walk through 3 production disasters end to end. Disaster 1, the client timeout, the most common payments incident in the world. The user taps pay. Your server receives the request, calls Stripe, Stripe captures the money, your server writes payments row status captured. Your server now sends 201 created back to the client. The mobile network drops on the way back. The client sees a connection timeout. The client library does the correct thing and automatically retries with the same idempotency key. Without idempotency, your server processes the second request as new and charges Stripe a second time. Double charge, angry customer, fraud chargeback. With idempotency, the second request hits the dedup table first, finds status completed with a matching request hash, returns the stored 201 response with the same payment ID. The client now sees success. Stripe was charged once. The ledger has 1 row. The customer sees 1 charge on their statement. The duplicate request was absorbed silently and correctly. This is exactly the scenario the interviewer wants you to walk through unprompted. Tell this story and you score a senior signal. Disaster 2, the duplicate webhook. Stripe sends you a webhook, charge.succeeded, with event ID EVT_123. Your handler processes it, credits the customer wallet by $50, returns 200 OK. But your 200 took 8 seconds because the database was under load. Stripe waits 5 seconds for an ACK, gives up, retries the exact same webhook. Now you receive event ID EVT_123 a second time. Without dedup on the event ID, you credit the wallet a second time. Customer now has a free $50 and your ledger is wrong. With dedup, the receiver runs insert into processed events with the event ID, on conflict do nothing. If 0 rows inserted, this event has been seen, return 200 immediately with no further processing. If 1 row inserted, process the credit and return 200. The processed events table is a separate dedup substrate from the request dedup table. Different surface, same pattern. Both are required. In the interview, name them both. Also mention that you always verify the webhook signature using the secret Stripe shares with you, to prevent attackers from forging events. Signature verification and event dedup together are the full webhook hardening story. Disaster 3, the subtlest of the 3, and the one that exposes whether you have actually run payment systems in production. Your server calls Stripe. Stripe captures the money successfully. Stripe tries to return 200 to you. The network drops. Your server thinks the call failed, marks the payment as failed in your ledger and rolls back. But Stripe has the money. Your books say 0, theirs say 50. This drift cannot be caught by idempotency keys, because there is no second request to deduplicate against. The drift is invisible until a customer complains or you go bankrupt. The fix is reconciliation. A nightly job, sometimes hourly, pulls the statement API from Stripe for the previous time window. For every charge in the gateway list, look it up in your ledger by payment intent ID. 3 outcomes. Match, do nothing. In Stripe not in ledger, auto-heal by inserting a missing payments row with status reconciled and a flag indicating the source. In ledger not in Stripe, alert the on-call, this is potential fraud, a code bug, or a refund you missed processing. Reconciliation is the safety net that converts eventual consistency into actually consistent. Without it, no payment system survives a month in production. One more topic the interviewer will probe, and it is what separates a passing answer from an offer. Your ledger itself. Beginner candidates design a payments table with a status column that gets updated as the payment moves through states. Senior candidates design an immutable event ledger. 2 tables. Payments, 1 row per intent, status derived from events not stored directly. Payment events, append only, 1 row per state transition, columns event ID, payment ID, event type which is one of initiated, captured, failed, refunded, disputed, amount, currency, timestamp, source. You never update an event row. You never delete one. The current state of any payment is computed by replaying its event stream. This pattern is event sourcing applied to money, and it gives you 4 powerful properties for free. 1. A complete audit log for compliance. 2. Time travel, you can ask what was the state of this payment yesterday at 3 p.m. 3. Trivial reconciliation, you replay the events. 4. Easy debugging of customer complaints from any point in time. When the interviewer asks how you would investigate a customer issue from 3 months ago, the answer is, I replay the events for that payment ID. Strong signal. Now the full production handler in 20 lines, the version you write if the interviewer asks for actual code. Begin transaction. Read idempotency-key header, return 400 if missing. Compute body hash with SHA-256. Insert into idempotency keys with key, customer ID, status new, request hash, on conflict do nothing. If inserted, skip to payment processing. Else, select for update the existing row. Branch on status. If completed in hash matches, commit and return the stored response. If completed in hash differs, commit and return 422. If in_progress, commit and return 409 with retry after 1. Otherwise failed, commit and return the stored failure response. Payment processing path. Insert into payments with status pending. Insert into payment events with event type initiated. Insert into outbox with target equals Stripe, payload equals amount plus customer plus a gateway idempotency key derived from our key. Update idempotency key set status equals completed, response equals payment object. Commit. Return 201 with the payment object. Worker thread, separately. Poll outbox every second. For each pending row, call Stripe with the gateway idempotency key. On success, insert payment events type captured, update payments status captured, update outbox status done. On failure, exponential backoff, max 5 retries, then DLQ with on-call alert. 20 lines, every edge case covered. The cheat card. 8 things to say in the FAANG LLD interview, in this exact order, and you walk out with an offer. 1. Define idempotency in 1 sentence using the elevator analogy. 2. Name the 4 sources of duplicates, double tap, network retry, browser back, webhook retry. 3. Sketch the API contract with idempotency-key as the only required header. 4. Draw the 4-state machine with new in progress completed failed, and emphasize a in progress as the critical concurrent state. 5. Pick Postgres as source of truth with a unique constraint on key plus customer ID for optimistic concurrency. 6. Explain the outbox pattern and why external calls live outside the database transaction. 7. Walk through one disaster end to end, the client timeout is the safest pick. 8. Mention the reconciliation job and the immutable event-sourced ledger. Hit all 8 in 20 minutes and the interviewer is writing strong hire. One sentence to memorize forever. Idempotency-key, dedup store, outbox, reconciliation, immutable ledger. 5 pieces. Same money, same result, every retry, every time. Now go build it.